Hello, welcome to session number 7 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam, and I'm going to talk today about a shunt element, a shunt inductor, right? And before I do that, I had some theory which is pending, which I wanted to clear. So what I wanted to clear was the following. Uh, let's say that we have a line, right? So we know that for a line, for a line, Zin was equal to e raised to gamma L plus minus gamma L divided by e raised to gamma L minus gamma of e raised to minus gamma L. Now I just wanted to do the following. E raised to gamma L is equal to cos hyperbolic gamma L plus sine hyperbolic gamma L. Now if gamma is equal to j beta, then Zn is equal to e raised to j beta L plus gamma e raised to minus j beta L divided by e raised to j beta L minus gamma e raised to minus j beta L. Now one more thing is, if I was to do a cos hyperbolic of j beta L, that will be equal to cos of beta L, and if I was to do sine hyperbolic of j beta L, then this will be equal to j sine of beta L. Now substituting that right into the equation, I would have cos of beta L plus j sine of beta L, okay, plus gamma times of, now cos of minus theta is cos theta, right? Yeah, so in this case it will be cos of beta L minus isn't it, minus j sine of beta L, right? And then here it will be cos of beta L plus j sine of beta L, okay, minus gamma times of cos of beta L minus j sine of beta L. Now let's assume that, so gamma basically is equal to ZL minus Z0 by ZL plus Z0. Now let us consider that the load ZL is equal to infinity. So basically this is a open circuited stub. Okay, so this is a open circuited stub. So for open circuited stub, I have gamma is equal to 1 by this and 1 by this, so it will be equal to 1, right? So if I do that, then I have Zin is equal to okay, so in this case it will be twice of cos of beta L divided by one, right? So minus plus, right? So it will be twice of j sine of beta L. That means that this is equal to 1 over j tan of beta L. Okay, there is a Z0 which I forgot here and here, right? Hang on, and here also I forgot a Z0, right? Okay, so then we have this as by Z0, or I can say that an open circuited line provides capacitance equal to, so this is equal to omega 10 beta L by Z0 is equal to omega c, right? So 1 over omega 10 of beta L by Z0. So this will be the capacitance. Now let's assume ZL is equal to 0. In that case, gamma is equal to ZL minus Z0 divided by ZL plus Z0. So this will be equal to minus 1. So in this case, Zin will be equal to twice of J twice of sine of beta L divided by twice of cos of beta L. Again there will be a Z0 cos of beta L. So basically this is equal to J tan of beta L Z0, correct? So this will be equal to omega L. So a short circuited line provides a inductance L, which is given by so this is omega L, right? So L will be equal to 1 over omega tan of beta L Z0 tan of beta L. So this would be L. So let me just outline that. So an open circuited stub can be used to provide capacitance. A short circuited stub can be used to provide inductance. So with this out of the way, okay, so this was just something which was left over. So now let us proceed to looking at a shunt inductor. Okay, so I am going to go here and make a new layout, and I will call this as shunt 1 nano Henry. Okay, shunt 1 nano Henry, right? Okay, so now we have a layout where I'm going to put the same inductor which I had done earlier, and this is going to be the one which is 1.2, this one, right? And say apply, and that's over here. Now I'm going to do a single port simulation and look at the shunt element. So I am going to go here to M1 and just add a ground plane. So let's say this is my ground plane, and I'm going to go from the center to the center, right? And I'm going to just keep the same size on both sides, so like we did for the last time, right? So I'm going to make sure that the ground extension on both sides are the same. Okay, this is done. Now what I want to do is I want to create a back via. So if you look at this, a shunt element, basically I am on metal 1 and a back via will connect it to, sorry, I'm on metal MET1 and the back via will connect me to metal 1 of the board. So this one, so let me just flatten this for a second. So hang on, right click component and say flatten. Okay, one level hierarchy. So if you see this one, okay, so this one is metal 1, right? So I need to put a via to go down, right? So I will take a back via. So that's a back via. Okay, now one thing I'll tell you, read the manual and look at if there is any restriction on the placement, and the restriction is on the placement of the what you call the gate fingers. So for here it's okay, but then your longest features are along the alignment keys. Okay, so because this is a non-self-aligned process, so move relative, so more on that when I later go into circuit designs, right? So let's say I want to take it off by 15 micron to the right. Okay, and then here I want to just connect M1. So on a metal 1 which is MET1, I'm just going to extend this up to here. So this is going to the via, right? Now you want to be sure that you are talking about metal 1, so I will say visible none, and I'm just looking at metal 1. So you see it is connected, right? So now I'm going to do visible all. Okay, so this is connected, and this one is going to the back plate. Okay, so let's say that's the black plate. Okay, so this is the situation where I have a single port simulation, and this is a shunt element. Let's see how. I'm going to put in a ports here. So this is one port, and this is its ground reference. So I'm going to move the ground reference underneath like this, and remove this line extension. So I have a ground port placed, and now I'm going to look at EM simulation. Right, let me make sure I'm recording. Yes. Okay, so now what I'm going to do is I'm going to go to port editor, and 2 is a ground reference for 1. So this is a single port simulation, right? Going back to the EM simulation setup. Okay, so we are all set, and then I'm going to do a FEM on this, right? Right, so everything looks okay, and I am going to simulate from 0 to, let's say, 48 adaptive. Okay, 48 gigahertz. And next is I want to make sure that all the frequencies are shaved. According to meshing, I'm going to go and say that use the finest mesh after you're done with convergence. Save the model, and then I'm going to hit simulate. Correct? So hit simulate. Now one more thing I want to make clear before I just let it simulate. So let it simulate. Okay, so one more thing I want to clear is, let's look at its EM preview, 3D EM preview. Okay, so EM preview is done. Okay, so that is my inductor, and that inductor basically is a shunt element through a via. Correct? Now I want to see the connectivity, because this should be a single metal. So there is this connectivity tool. So if I was to choose metal 1, so see, everything is connected here, so it has shaded everything, right? So that is a very good tool to make sure that you have a connectivity. So I'm done with the preview, and I'm going to let this simulate and put the recording to pause. Okay, the simulation is done, and here we have a single port S parameter simulation results, and I'm going to put a marker here. Okay, so I see here, let's normalize this to 50 ohm, right? And look at the DC resistance. So the DC resistance is 1.045. Okay, so we are done with this simulation. Now I want to see what are the inductor values. So what I'll do is I will do a S to Z conversion. Okay, and as it is a single port, I would have a very simple equation. S to Z of S, and there is only one parameter in S, right? And then I would just say the shunt value of the inductor, right? So that shunt value LSH would be equal to imaginary of Z, correct, divided by 2 pi frequency, 2 into pi into frequency, bracket close. So this will be the shunt value of the inductor. Okay, so let's see what has happened. Okay, ZS, not Z, ZS. Yeah, so that's the shunt value of the inductor. And let's look at the real part of the RS. So let's look at RS. RS would be equal to real of ZS. Real of ZS. Right? Okay, so now let's plot them. Okay, so we have inductor value, which is LSH. Okay, so clearly you can see that there is a resonance coming because of the shunt elements, not the series element, which was very unclear in case of a series or a two-port simulation, right? So this occurs at 21.25, right? Okay, so this occurs at 21.25. And what I want to see here is the following. I want to see what is the inductance at my frequency of interest, which is 10 gigahertz, or let's say at very low value, for example, let's say over here. Okay, so at over here it is 1.15 nanohenry, right? Now let's put here the RS, or equivalent series resistance, and I'll put it on the right hand side axis. Okay, so you can see that this is reflecting the resonance, anti-resonance, right? So let me just, okay, and somewhere over here the value is around 1.045, but let's look at 10 gigahertz, what that is. Or let's say over here itself, where I'm checking L, it's 2.5 or 2.47 or whatever, right? Roughly at that frequency is that. Now if I was to do a shunt model, I already have a lot of stuff. Only thing is I want to find out what is the shunt value of capacitance. So the shunt value of capacitance will be CSH, will be equal to 1 divided by 4 times of something square. Okay, so that something square would be pi, 4 pi square into something square again. Okay, something square again, that is going to be the frequency, which is 21.25, right? 21.25 gigahertz, right? That is that into the L value, right? The L value is 1.115 e minus 9, right? 1.115 e minus 9. So this would be the shunt capacitance, okay, which will cause this anti-resonance to occur. So let's look at its value. Its value would be CSH. Okay, so let's check its value. Its value is roughly 50.3 femtofarad, right? So that's its value. Now I'm going to very quickly put together a model and try to see if that model works right. So I will go here to, okay, I'll go here to create a test shunt inductor as another schematic, and here I'll start putting the model. Okay, so the inductor value turns out to be 1.115, correct? 1.115, and the DC resistance is 1.045. And as far as the variable, I will go to the series model, and I'll just copy this, edit, copy, and I will just paste it over here, edit, paste. Okay, and I'll just rotate this. That is the frequency dependent resistance, and the shunt value of the capacitor is around 50. Okay, I'm going to throw in 55, roughly 55 femtofarad. Okay, so later I'll tune this to get the match. So this is going to be my shunt equivalent model for a shunt. So it will be a shunt model for a inductor using single port simulation. So let me do the simulation. So I'll put here S11. So I'm going to put here S11, and I'm going to do S parameter simulation from 0 to 48 gigahertz in steps of, let's say, 10 megahertz, apply. Okay, so I'm ready for the simulation. Anything else? Nothing. Okay, so I'm going to hit simulate. So I'm going to plot here S11, and I'm also going to plot S11 from the EM simulation, right? So from EM simulation over here, I plot S11. So it's almost very close, other than in some mid frequencies it's slightly off, but more or less it's the same. Let's look at the values for shunt inductor. So now what I'll do is I'll just copy the equations from here. So these equations I'm interested in. Okay, Control C, and then over here Control V. So now these are referring to my model, not my EM, right? So I am going to plot here the LS values, LSH. So this is my model. So my model is like this. Now on top of it I want to put the other one. So I will copy this, and I am going to use the S parameter of the EM simulation. So that's the EM simulation, that's the S parameter. Okay, so that is ZS1. Then LSH1 is going to be my EM simulation, right? So this will be ZS1 divided by 2 pi frequency. So frequency has to come from that scale which is used for the EM simulation, right? So that's the frequency. So that's LSH1, and the real part would be the resistance, which will be from ZS1. So now these are equivalent to, so let's put here first of all let's put here RS. So this is model. Let's put this on the right side axis. So the solid curve is the model, right? So let's just do this, and then I'm going to put here LSH1, which is from EM simulation, and make it dotted. So I'll make it red. Let's first see how this turns out to be. So it has come up, so the capacitance is high, right? Because we put 55. We should not be putting 55, but still let's go here and let's make this one as dotted, short dash. Okay, so this is my EM and this is my model. It's not matching because instead of 50 I'm putting 55. So let's put back what I computed for 50, right, and simulate again. Okay, so now it is correctly matches, right? So that was a detour which I took, was not, you know, what was not expected. Now let's look at the series resistance in case of EM simulation, and that also matches, but I have to put it on the right hand side axis. Trace right hand side axis. Yeah, so it matches. It's just that I have to put it dotted. So I'm going to put blue, and I am going to put short dash. Okay, so it kind of matches the height also. So basically you have to just write the equations and you will be as accurate as this, right? If not more accurate. The resistance comes out to be slightly smaller, bigger, right? So it has to be reduced. It was 2.5 roughly, right? No, okay, 2.7, 2.8, let's say. It is less lossy, right? Okay, it's almost to the same height, right? Let's zoom into this portion. Okay, so the capacitor has to be slightly smaller, right? So let's say 49.5. No, slightly bigger, 50.5. 50, sorry, 50.5. let's say what we had in our calculation. In our calculation is 50.3 actually. So let's put here 50.3. So the formulas are very accurate, because if you know the physics, then formulas will be accurate always. It has to be further increased. The dotted one is coming from the model, right? The dotted one is coming from the model. The dotted one is coming from the model. Oh, the dotted one is coming from the model, is it? Oh, no, the dotted one is coming from the EM, right? So we are going the wrong way. The dotted one is coming from the EM. Yeah, now better. 49.5. Okay, almost there. Okay, and so 50 is anyways the right number, and this one has to go up. Okay, now it has come earlier. That is 50.3. Let's see what final values we come up with. 50.3. No, somewhere in between. So that's the right number, I think, roughly. It hardly matters, right? Okay, so I think I'm gonna stop here. Okay, so this is going to be the EM versus modeled, and this EM versus modeled is based on certain equations, and now you can probably understand the power of equations versus your deep learning stuff, right, where you just give the training sequence, right? That is blind, right? So really, don't want young generation to apply AI and deep learning to everything, because they will not know the physics of what's going on, right? And the sense of accomplishment will not be there, because you are not doing the stuff, right? Some stupid number crunching computer is doing your stuff, right? And they call it modeling, I call it searching, right? So you are searching something versus you are modeling something, right? So a deep learning is a deep search. That's it. It is not basically intelligent. It's a dumb program, right? And you call it AI, right? So anyways, you be intelligent and apply the physics to the model. So now let's see how much time do I have. Okay, so what I'm going to do is I'm going to stop here. This is a small session. I just showed you how to how to model a shunt inductor. So a shunt model versus a series model. So this is a shunt model of an inductor. This is based on single port simulation, and then this one was the series model, right? This one was the series model for a series inductor. This is the shunt model for the inductor. So I'm going to stop here for this small session. As far as the MIM capacitor, it is going to follow the same set of equations, right? It's just that, instead of j omega L, now you are dealing with 1 over j omega C. So as a simple modification, if you try it, you will get it. So I don't want to do a MIM capacitor series and shunt. I will leave it to the audience to do their series and shunt capacitor modeling, right? So thanks a lot. Thank you very much.